Hey guys, this is part 2 of Lab 7. So we're going to talk about PID controllers. How you do them is pretty much how you do PD controllers, except for you add an I. So first you design the PD part, and then you add the I part, and then via a PI controller, and then you multiply the PD controller and the PI controller together, and that gives you a PID controller. So here's our example. We have this, right? Our requirements is our peak time needs to be reduced by a third, our percent overshoot needs to be 20%, and we want zero steady state error. So this part, these requirements can actually be fulfilled with just a PD controller, but this zero steady state error part needs an I controller for the same reason here, right? So it can satisfy, maybe some requirements, but we're not going to get steady state error without having this FAM, without having an integral gain control. Okay, so we're going to do the same thing that we did last time. Here is the new transfer function, G. So I'm going to run this, open sysotool. Here we have it. Great, so I'm going to, just like I did last time, import the G from the workspace. Great, and we get this root locus here. And we want our overshoot to be 20%, so I'm going to add that. Okay, same as before. We see this is doable for the system we have, right? For a value of k, this is doable. For a value of k that is equal to, right now c is just k, right? We haven't added anything else yet. So if c or k is like 4, no, 40, more than that, 100, around here. If k is 120, then we get a overshoot of 20%. That's good to know. But we also want to reduce the peak time by a third. So we want a peak time that is 2/3 of the original peak time. Now we don't have a system requirement for peak time. So we can't just plot, we can't just see what the peak time is here, unfortunately, and then change it to 2/3 of that. What we need to do is convert peak time, given our overshoot, to frequency, because we can plot natural frequency. So we do that, just a little bit of math. So overshoot 20%. From that we can get directly a zeta. We know our peak time is half of a wavelength for a sine function. It's just that first hump, right? So it's just how long it takes to get that first peak. So that's that peak is going to be of the damped frequency. So what we want to do is get natural frequency out of that. So we convert damped frequency to natural frequency. Now we know zeta, and if we come here, we can find that natural frequency. At that point, we're getting 11.8. That's what I got last time too. So at our, for a k value that gives us an overshoot of 20%, our natural frequency is 11.8. And so what that provides us with is we can then get our peak time of 0.3. We want 2/3 of 0.3. So our new peak time is going to be 0.2. And from that, since we know that we want our overshoot to be 20%, which means that we have the same zeta as before, we can get our new natural frequency of 17.64. So I'm going to move this over to 17.64, and we'll see that our circle moves away. Right, so now it no longer intersects, and we have to do something about it. Right, because there's no way that we get that the root locus goes through this point. There's no way that we get this overshoot of 20% and this natural frequency, which corresponds to a peak time of 0.2. So we need to add a 0. So we do that the same way we did before. Here's our 0 for our PD controller. We're going to move it so it intersects, so the root locus intersects with the overshoot and natural frequency lines there. That looks good enough. Okay, so I'm going to zoom in on the intersection. Maybe more. Okay. So that's great. We've added a 0 such that our root locus now goes through this intersection. Where was our 0? Looks like it was placed at negative 56.3. When I did it last time, it was negative 57. I'm just going to go with that. So I'm going to change this to negative 57. It's probably not going to change this guy too much. Okay, and we want our loop gain. So that way we're looking at this point, right? So by adding a 0, now it is possible that our system goes through this point. We need to specify what the parameter is such that we get this point specifically, or the point we want specifically. So I'm just going to increase this. Oops, I forgot to do something. So I like this format better. I think it actually tells you to do this. Go to Preferences, Options, go to this 0 pole gain one. Basically, it just lets you easily figure out what poles are. It's not clear here, right? It's going to be inverse of this 0 is going to be the inverse of 0.018. This will just tell you. So if I go here, click OK. Let me reopen this. Right, now we see, oh, it's 57. Okay. What value did I get for the loop gain? Looks like 4.38. Oops. Oh, that was right. 4.38. Don't know why it didn't work last time. Well, it looks like 5 suits us better. 5.1. I'll just do 5. Okay, so now we've selected that intersection more or less. I did it last time, it was more like 4.4-ish. Now it's 5. Has to do with how specifically or how accurately you line up the intersections. Anyways, so that's great. We've done the PD part, right? We found the pole or the 0 location of negative 57 and our loop gain of 4.38. Here is 5, but we're just going to go with what I had before. What does our response look like? Looks like we have some steady state error, right? Because we have a step input, which is inputting just a bunch of 1s, right? So our R of S is just a bunch of 1s. We want to command it to a value of 1, and it looks like that we're getting a steady state value of 0.93. So our error is about 0.7, and we don't want that. We want an error of 0. So now we'll talk about the PI controller.